In this video, we're going to be introducing a sequence and talk about what sequences are. We'll start with the definition. A sequence is simply a function with only the set of natural numbers, or perhaps the first n natural numbers, for its domain. If the domain of a sequence is the first n natural numbers, then we say we have a finite sequence. If the domain is the entire set of real numbers with outputs in R, okay, that's a symbol for the set of real numbers. However, the outputs could be other things besides just real numbers. They could be complex numbers or vectors or matrices or other things, not necessarily even mathematical things, just anything. Since the domain is automatically set when we consider sequences, we often only list the second coordinates instead of a fuller table. Also, we often use a sub k to represent a of k, that is, the kth a value or the second coordinate when the first coordinate is k. That's usually written as a sub k rather than a of k, like we would for most functions. We also have some variable conventions. For general relations, the generic variables for input and output are x and y respectively. For functions, we typically use letters from the middle of the alphabet, such as F, G, or H, for the labels for the second coordinate, usually with F being the first choice. So we can name functions F, or G, or H. But we keep X as the generic input variable. In sequences, the input variable is typically either I, J, K, N, or M, and the output variable is chosen usually from the beginning of the alphabet, such as A, B, C, or D, usually lowercase. Of course, these are just the generic choices for variables. We can actually use any variable for our choice. In a specific context, we typically choose variables suggested by their meaning. For example, we would prefer to use t for time and v for velocity if that's what we are dealing with. Remember that variables are case sensitive. The variables lowercase a and uppercase a here are two different variables. So let's look at an example. For example, we can take the function a, which maps the set of natural numbers into the set of real numbers. By the way, that's the symbol for the set of natural numbers. Remember, natural numbers are 1, 2, 3, 4, 5, 6, 7, so on, counting numbers. And such that where it's given by a rule, a sub k equals 3 times k. And that generates the following table of values with both inputs and outputs. Since it's a sequence, that means this input is, the domain is a set of natural numbers. The first part of our table is automatic. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. And the formula tells us we just take the k value and multiply by 3 to get the corresponding y value or a value here. So when the input is 4, the output is 12. A sub 4 is 12. So these are the 3, 6, 9 is A1, A2, and A3. So as is usually the case with function, this table only gives a representative piece of the actual infinite table. However, notice that for any sequence, the first line of the table is always the same. So we usually reduce the table to just being the second part. So in other words, this part up here is automatic. So we just leave it out and we only keep this part here. Instead of writing it in the table, we write it with commas. And so we just write down the outputs 3, 6, 9, 12, 15, 18, 21, and so forth. Now notice, like most tables, this thing goes on forever. However, this one goes on forever only to the right, not to the left. Another thing that's different about this than, say, y equals 3x, which we're thinking more in terms of the generic, letting x and y be any real numbers, then is that there's nothing in between these points. There's nothing between 1, 3, and 2, 6. So when we graph this, we plot the dots like we would with any graph on a Cartesian coordinate system here. Here's 1, 3, and 2, 6, and 4, 8, and so forth. Okay. I'm sorry. 1, 3, 2, 6, and 3, 9. 4, 12, 5, 15. You can see those on the graph. But what we have here is a bunch of isolated dots. These are called isolated points. So know what that means is you can draw a little circle around the point, and within that circle, if it's small enough, the only point of the graph will be that one dot. So it's isolated. We do not connect the dots. So this is the first dot here. There's at 1, 3. There is nothing to the left or below this. They do go up and to the right forever. In this particular one, they happen to line up in a straight line because every time we go to the right one, we're going up 3. So that makes it go up in a straight line. So if we were to extend the domain to be all real numbers and connect the dots, we would get y equals 3x. We would get a line here. That's not what we have here. We only have just dots along that line. So here's an example for you to work out. Let's see. I already gave it away there. Okay. Write out the first 7 terms of the following sequence and graph it. B sub k equals 3k squared. So work this out yourself and press pause and come back. Press pause now. Okay, let's see. Start with k is 1. 1 square is 1 times 3 is 3. 2 square is 4 times 3 is 12. 3 square is 9 times 3 is 27. 4 square is 16 times 3 is 48. 5 square is 25 times 3 is 75. 6 square is 36 times 3 is 108. And 7 square is 49 times 3 is 147, and then so forth. This continues on. You could easily do that by hand. I'll show you how you can use some technology as well. Now, of course, we could graph these on a piece of graph paper pretty easily as well. But I want to introduce some technology here as well in this video. We're going to talk about sequences in GeoGebra. In GeoGebra, we can make sure that the algebra view is visible and the graphing view. So you could start with a classic GeoGebra, or you could start with the graphing GeoGebra, but you have an algebra view here and a graphing view here. So in the algebra view, we use the sequence command to produce a finite sequence for any GeoGebra objects. The objects we want here are points. So we can do sequence. You just type in the input box here, sequence, open parentheses. And then we want a point, open parentheses. First coordinate is k, comma. Second coordinate is 3k squared, close parentheses. You can get up to the square by hitting the Shift 6 and then typing the 2. Then I think you have to put a right arrow to get out of the exponent, possibly to put the close parentheses. Then comma, k, comma 1, comma 100, close parentheses. So this will generate, well, the first 100 terms. It'll actually be a finite sequence of points, but that's going to be more than we're going to graph here anyway. Whereas in reality, this thing would go from 1 to infinity, not just to 1 to 100. But in any event, we can graph that here, and this is what the graph looks like. Now, it's going to default to a square scale. In this case, to see it a little bit better, I decided not to use a square scale. So a couple things you can do when you're over here in the graphing menu, you can click in here and left click and drag this around so that we're only showing the first quadrant. Notice since this is a sequence, we automatically know the domain is 1, 2, 3, 4, 5, 6, 7, and so forth. So we're not going to have anything on the y-axis. We're not going to have anything where x is negative. So we're not going to, or k is negative. We're not going to have anything in the second or third quadrants. Everything's going to be in the first or fourth quadrants because the outputs could possibly be positive or negative. Now in this particular sequence, outputs are only positive, so it's first quadrant only. So notice I dragged this around so that kind of put the origin down close to the lower left corner of my little window here. So we're seeing basically just the first quadrant. Now I can use my scroll wheel on the mouse to zoom in and out as needed. Also, I can change the aspect ratio. If you'll right click out here in the open region on the graphing menu, one of the things that will come up is the ability to change the aspect ratio. Here I'm using a 1 to 100 aspect ratio between the ratio between the x and y axes. And you can use this, like I said, you can use the scroll wheel to zoom in and out. So a little playing around with that, I was able to come up with this graph, which I think shows a pretty good idea of what's going on. And you can see the shape that's being formed here. But again, it's isolated dots. This is the first one here at whatever it was, 1, 3. Then it goes to 212, 327, and so forth. It is not, we do not connect the dots, right? They're all isolated points. There is a first one here on the lower left, and there's nothing to the left or below that, but they do go up and to the right forever. If we were to connect these dots, we would have us a nice little parabola. And so these are for part of a parabola. Now that was using GeoGebra, a computer program. We can also look at sequences on a graphing calculator. So we can use a TI graphing calculator to graph sequences as well. First, press mode and select sequence on the first line. When you get mode, you'll see this screen here. We can choose function, parametric, polar, or sequence graphing. So if we select this one here. Now if we press y equals, normally it comes up y1 equals, y2 equals. That's when you're in function mode, because that's y is a function of x. You should be able to solve for the output variable. We're going to call them y1, y2, y3. But here we have sequences u, v, w, and the input variable the calculator is going to use is n instead of x, or I like to use k when I write them, but it's going to use n. So we put in the formula 3n squared. Overall, n's are going to start at 1, and this specific sequence are going to start at 1. So we enter that in. Well, how do you get the n? We just push the xt theta button. So when you're looking here, this button right here, if the mode is in sequence mode, when I push the xt theta in button, I get n. You're probably used to that being x when you push that button, because that's what it is in function mode. If you're in parametric mode, that would be t when you push that button. If it's in polar mode, pushing that button will give you theta. In sequence mode, it's going to give you this little script n. Because x, t, theta, and n are the default variables for functions, parametric functions, polar functions, and sequence functions. Okay, at least on this calculator. You can hit table setup, tell the table to start at 1 and go up by 1, put these on automatic, and the table will show, it'll show you the first 7 ends and the corresponding outputs here. If you scroll up to 0 or negative, it will give you an error message here, so it's undefined. But we can scroll down to see more terms, the 8th or 9th, 10th, 11th term. So that's one way to get the terms with technology that we did by hand up here. Let's see here. Why did it return 1? Hang on a minute. Okay, I fixed it now. What the problem was is this will, if you put something on this line right here, that's going to force a particular term to start with. And this is useful for doing I think it will do recursive functions. We'll try that a little bit later. But we should have had that cleared out right there. And then the formula does produce the right thing, which is 3, which is the appropriate thing. Okay, and so we can see that. We can change the window if we want here, and then we can see the graph here. Okay, here's another one for you to try. So write out the first 7 terms of the following sequence and graph it. A sub k is -1 to the k plus 1 power times parentheses 2k plus 1, close parentheses, that's the numerator, and divide that by 2 to the power k, that's the denominator. Work this out yourself, come back when you're finished. Press pause now. So the first thing I want to point out is that -1 to the k plus 1 is going to give us an alternating sign. When k is 1, you get 1 plus 1 is 2. -1 to an even power is +1, so that's going to give you a positive term. But being 1 times the rest, it's not going to affect the value of the rest of it. If I plug in k is 2, 2 plus 1 is 3. -1 to the third power is a -1. And so that's going to give us a negative, whatever the rest of it is. And likewise, if it continues to go forth alternating in sign, so that every time you put an odd number in for k, k plus 1 is even, and the -1 to that power is +1. Whereas if k is even, k plus 1 is odd, and so -1 to the odd power is -1. So this starts with a positive, and then just alternates sign. Positive, negative, positive, negative, positive, negative, positive, negative, and so forth. So now that we've done that, I've written the signs down. Let's worry about the rest of the fractions that we get here. So let's plug in k is 1. 2 times 1 is 2, plus 1 is 3 for the numerator for the first one. 2 to the first power is 2. That's the denominator for the first one. So the first term is positive 3/2. Plug in k is 2. 2 times 2 is 4, plus 1 is 5 for the numerator. 2 to the second power is 4 for the denominator, so we get -5/4. For the next one, we plug in 3. 2 times 3 is 6, plus 1 is 7. That's the numerator. 2 to the third power is 8 here. And so forth, we can fill out these. But I also want you to notice there's a pattern here. That's a linear type equation, so you should know this pattern. We're just adding 2 to each one to get the next. 3 plus 2 is 5, 5 plus 2 is 7, 7 plus 2 is 9, then goes 11, 13, 15 for the top. And there's a pattern in the bottom too, but it's geometric or exponential pattern where we're multiplying by 2 each time. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, then 32, 64, and 128, doubling the denominator each time. So there's a nice pattern to the denominator, a different nice pattern for the numerator, and an alternating pattern for the sign. So a lot of things we're going to do in calculus, this doing -1 to the k plus 1 or -1 to the k gives us an alternating sign. -1 to the k plus 1 is going to start with a positive and then go negative. So it'll be positive, negative, positive, negative. Where if you just had -1 to the k, it would be negative first, then positive, negative, positive, negative, positive. Another thing you might notice is the top and bottom are both getting bigger and bigger, but the bottom's getting a lot bigger, a lot faster than the top. So the absolute value of these fractions is getting smaller and smaller each time. So this will actually have a limit of infinity. That's going to be a key calculus idea for us with sequences as we go forward. So here I used GeoGebra to go ahead and work this out. So I'd use the sequence command, parentheses, parentheses, basically just type it in like it looks, k, comma, and then type the formula in like it looked what it was given, close parentheses, comma, k, comma 1 to comma 20. So this will be the first 20 terms, which I think you see graphed here. So notice the first one was, what was the first one? It was 3/2 and -5/4. So 3/2 is up here. Then -5/4 was down here. It goes to the other side of the axis up here. So it keeps alternating between first quadrant, fourth, first, fourth, first, fourth. But the amount it's going up and down each time is less and less and less. At some point, it gets to where we visually can't tell these points apart from the x-axis, but in fact, they are always either above or below the x-axis by a little bit. But you can get a good idea what that looks like on the graph here. In the next video, we'll come back and talk about how we can not only use an explicit formula, but a recursive formula to write down sequences.